Our first area of study in the unit on rotational motion has to do with what we call angular kinematics. So let me remind you a little bit about our study of kinematics from the beginning of the semester. We defined average velocity, so that's what when we put the bar on top of the v, that's our way of saying average velocity. Average velocity is equal to, by definition, so 3 lines in our equal sign is our way of saying this is an equality by definition. Average velocity is defined as a change in position divided by time, which is why it's measured in meters per second. Instantaneous velocity is defined as the limit as time approaches 0 of dx dt. Let's come back to this expression. In the case of uniform acceleration, average velocity is also nothing more than the average of your starting velocity and your final velocity. In other words, add your starting velocity and your final velocity together and divide by 2 to get the average velocity. So if we put these two together, we can say that delta x, or displacement, is equal to average velocity times time. That just comes from multiplying both sides of this equation by t. But then we can substitute in place of average velocity, and we get delta x equals 1/2 v naught plus v times t. And you recognize that as one of the kinematics equations that we've put in practice several times throughout the semester. We defined average acceleration as change in velocity divided by time. If we multiply both sides of that expression by t, we can say change in velocity is acceleration times time, and change in velocity is nothing more than the final velocity minus the initial velocity. So we can get an equation that says final velocity is initial velocity plus acceleration times time, and you recognize that as another kinematics equation. By the way, instantaneous acceleration is also a derivative in its dv dt limit as dt approaches 0. Okay, so when we take this equation and combine them, we can get two other equations, and I would encourage you to review your notes from earlier in the semester to see where the equation delta x equals v naught t plus 1/2 at squared comes from, and v squared equals v naught squared plus 2a delta x. So that's just a quick review of where the 4 kinematics equations come from for describing motion in a straight line. So let's get into our study of angular kinematics and come up with a new definition. If an object is moving along a circular path, maybe this is it could be a spot of mud that's stuck to the perimeter of a bicycle wheel, and it advances from one point to another. Or maybe this is a lump of clay on the perimeter of a potter's wheel. Or maybe this represents a look down at the North Pole for a person who's standing on the equator as the Earth rotates on its axis through some angle theta. So we've got a value of s, which is the displacement along the perimeter, and then there's a value of r, which remains constant no matter where the object is located. So we're going to define the speed with which the object spins, and that's not the letter w, that's the Greek letter omega. So w looks more like that, omega looks more like that. Anyhow, we're defining angular velocity. That's what omega symbolizes. Angular velocity. It's defined as change in angular displacement divided by time. So notice the similarity to our definition for good old-fashioned velocity. Change in linear position divided by time. Angular velocity is defined as change in angular position divided by time. Instantaneous velocity is dx dt. Instantaneous angular velocity is d theta dt. So just as the units for velocity are meters per second, the units for angular velocity are radians per second. Now there's some alternative units. Sometimes we talk about miles per hour, or you can have something like inches per day. As long as you have some amount of displacement divided by time, miles over hours, inches over days, those are all valid, but we prefer meters per second. So our preferred units for angular kinematics are radians per second, but you could have something like degrees per day, you could have revolutions per minute, which we often just refer to as an RPM, right? So there's a new quantity defined. Now, if we stick to the situation where acceleration is uniform, then we can also define average angular velocity as the average value of some initial and final angular velocities added together. So we multiply both sides of the equation by time, and we find that the change in angular position, or the angular displacement, is the average angular speed multiplied by time, and then we substitute in place of average angular speed to come up with a kinematics equation for angular motion that says angular displacement is equal to 1/2 the initial angular speed plus the final angular speed multiplied by time. Notice the similarity. Looks an awful lot like this equation. We've just replaced the variables. In place of x, we have theta, and in place of initial and final values of v, we have initial and final values of omega. Let's carry on. We're going to define something known as angular acceleration. Let's define angular acceleration as the change in angular speed divided by time. And by the way, the instantaneous angular acceleration is the derivative of angular speed with respect to time. So we multiply both sides of the equation by t, and we find the change in angular velocity is the angular acceleration multiplied by time. Change in angular velocity should be the final angular velocity minus the initial angular velocity. And when we rearrange, we can state the equation. Final angular velocity is initial angular velocity plus acceleration times time. So we have a second kinematics equation for objects that spin around in circular paths. Whether this is, when I was a child, I played with my record player probably more often by putting toys on it than actually spinning albums on it. And I'd take toys and put them on the edge of my record player and let it spin around. And if they spun too fast, they'd follow the law of inertia and try to fly off in a straight line path. In any case, whatever you picture as the object that's spinning around, we have equations that we can use to describe how change in position and acceleration and time and speed all work together. So that's what we're working toward, coming up with a set of equations that describe motion for objects that move in circular paths. If we find a way to combine the two equations, we can make two more kinematics equations. There's a kinematics equation that says the angular displacement can be found by multiplying the initial angular speed times time and adding to it 1/2 angular acceleration times time squared. Notice the similarity between that equation and the equation for linear motion that says linear displacement is equal to initial velocity times time plus 1/2 a t squared. In fact, we have another linear equation that says final velocity squared equals initial velocity squared plus 2a delta x. So you might be able to guess at our fourth and final angular kinematics equation. Final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times angular displacement. So let's just review by taking a quick look at our four equations and compare side by side. Linear motion compared to angular or rotational motion. Displacement is equal to 1/2 initial velocity plus final velocity times time. Final velocity is equal to initial velocity plus acceleration times time. Displacement is initial velocity times time plus 1/2 at squared, and final velocity squared equals initial velocity squared plus 2a delta x. Likewise, we have a new equation that says angular displacement measured in radians is equal to 1/2 the initial angular speed plus the final angular speed multiplied by time. Final angular speed equals initial angular speed plus angular acceleration multiplied by time. Angular displacement is initial angular speed multiplied by time plus 1/2 alpha t squared. And finally, final angular speed equals initial angular speed squared plus 2 times angular acceleration times the angular displacement. Delta x is measured in meters. Initial velocity and final velocity are both measured in meters per second. Acceleration is measured in meters per second, which is equivalent to a meter per second squared. And of course, time is measured in seconds. When it comes to rotational or angular motion, displacement is measured in radians. Initial velocity or final velocity are both measured in radians per second. Angular acceleration is radians per second, which is equivalent to a radian per second squared. And time, of course, is measured, as always, in seconds. At this point, it's probably a good idea to review what a radian actually is. So we can state that 1 radian is approximately equal to 57.3 degrees, and we can show that graphically by drawing the unit circle and noting that an object would have to displace about that far along the perimeter of the circular path so that the path length s and the radius r are equal. If s is equal to r, then the angular displacement theta is equal to exactly 1 radian. And that looks about right. That's about 57 degrees. Now, where can we get 57.3 from exactly? Let's compare two values we know. If an object were to rotate farther along the perimeter of the circle so that it gets to the opposite side, then S is definitely greater than R, right? The path length is much more than the radius. In fact, how much greater is it? It's about 314% greater. By rotating around to the opposite side, you say we've gone 180 degrees. Another way of saying it's 314% greater, we say S is equal to 3.14 times R. So 3.14 is to 180 as theta is to 1 radian.